Good afternoon, everyone. Once again, this is Mr. Steele. I'm here to continue working through the analysis review for 2019. This will be the second part of a video series. It could contain even more parts than that. I'm not sure how long I'll be able to go, but I was just laying down, so I've got a little bit more energy and stamina to kind of stand up here. So without further ado, let's jump in. Once again, though, I know that I will be linking to the individual problems on the the PDF of the document. So if you want to find a particular one, you can go through that way. With that said, the first problem we're going to look at is question number 5. So question number 5 talks about some differentiable and strictly increasing function g of x. So right off the bat, I'm going to start there, and I'll use some different colors here. It says g is both differentiable and strictly increasing for all x values. It definitely doesn't say I just drew a straight line, because I did not. So let's start with that piece of information. If g is differentiable and strictly increasing, that tells us right off the bat that g prime of x is always greater than 0. Not or equal to 0, but literally greater than 0. It's always positive. So taking that into account, that's true for all x. And again, that's what that little upside down a means, is for all. So for all x that are out there in terms of the reals. So in other words, no matter what we put into g, g prime will end up being positive. So keep that in mind. The next piece that it tells us is that we've got a redefinition situation. Tells us that h of x is g of 4x squared minus 48x. So right down there, I'm going to write that down. Right down there, I'm going to write that down. I don't know. I have kind of a headache right now. So from here, basically that's the relationship we have. The question that we're asked then is on what interval is h strictly increasing? So in other words, where is this function going to always have its graph increasing? So in order to get there, as you might expect, it gives you a hint. It mentions the chain rule. But if you're trying to figure out where to go, we know information about g prime. Let's go ahead and just differentiate this. That's the key to figuring out where h is strictly increasing, which, by the way, would be true when h prime of x is greater than 0. So differentiating here, it does say that this is a chain rule problem. And it is a chain rule problem, but what I'm going to do to make this go a little faster is I'm going to do the substitution kind of in my head. We'll let u be the inside, and then the derivative of the outside is just g prime. So it'll be g prime of u. And then we're going to be multiplying times the derivative of u prime. Using parentheses, by the way, make sure they're there. Derivative of the inside, as is 8x minus 48. So basically there is our derivative. Now we want to figure out when this particular thing is equal to 0. And that gives us two possibilities. So the two things that could happen there is it could be that g prime of 4x squared minus 48x is equal to 0, or it could be that 8x minus 48 is equal to 0. And again, what we're looking for here is basically critical numbers. We're trying to find the critical numbers of h. So in looking at that, we're looking at the derivative. We're using the zero products property to determine the two possibilities here. But what I notice right off the bat is that this first one is impossible. Now you might ask yourself, why is it impossible? Well, the reason is that we said that g prime of anything is always greater than or equal or greater than 0. So g prime of stuff is greater than 0. No matter what excuse me. No matter what that stuff is, g prime of that stuff will be positive. So that means that this first equation contributes no potential critical numbers to us. It means our only other possibility is the second one, where I think it's pretty clear that x is equal to 6. So that means that for this situation, for h of x, we only have a single critical number. So if we try to set up a quick sign chart here, and we break it up at the single critical number 6, and we compare it to values of h prime, then we've got possibilities for when x is less than 6 and possibilities when x is greater than 6. Now with that said, thinking about what those possibilities are, we look at our ingredients here. The derivative of h prime is g prime of stuff times 8x minus 48. Well, if we take a number like 0, we'll have g prime of something. Actually, if we can say it right here, it's g prime of 0 times negative 48. Well, looking at that, g prime of 0 is positive. We're multiplying it times a negative. That means that h prime is negative. It has to be, because g prime of anything is positive. Likewise, on the other side, if we plug in 42, we'll get g prime of something. I'll just put a number in there because it doesn't matter. It's going to be g prime is going to be positive there. And then finally, if we plug in 42, we're going to have a huge number. I think that's 336 minus 48, whatever it is. It's positive. And we'll have positive times positive, which makes the derivative positive for h, for x values greater than 6. Now from here, we were interested in finding where h is strictly increasing. So h is strictly increasing for wherever this is. So we'll say for x greater than 6. And our reason would be because h prime of x is greater than 0. So there is our work and our explanation. So again, kind of weird. This one definitely feels a little uncomfortable, I'm sure. But again, our strategy was basically to use the chain rule to differentiate the function, and then to use the information they provided to find the critical numbers and figure out how we could do some sign analysis. Now, as a heads up, I had a student a few years ago named Mighty Chen. Mighty's actually potentially going into the classroom after, I believe, this year, which is pretty cool. Possibly teaching math as well, which is neat. Doing some great work at UC Merced. But what Mighty did when he took this test was he thought to himself, not sure what to do, but it says that I have a strictly increasing function g of x. So he picked a strictly increasing function to use. And he said, okay, well, let's figure out where that one is strictly increasing. So in here, if that's g of x, g of 4x squared minus 48x is going to be equal to 4x squared minus 48x. And that's going to be differentiated then. The derivative of this, which we called h prime, would be equal to 8x minus 48. And then he could clearly see that this is greater than 0 when x is greater than 6. So basically what Mighty did was he chose to just kind of pick an example and go from there, which is perfectly valid. Just make sure that you, like Mighty, choose an actually always strictly increasing function. So with that said, there's another alternative way. This is a mighty fine way to solve the problem. And in fact, I still remember Mighty doing that. It's the first student and only student I've ever seen do it. But there's another option in case 5 feels a little off to you. The next set of problems we're going to look at, I'm going to go through a little bit faster while trying to be as comprehensive as can be. These all focus around finding the x values guaranteed by the mean value theorem. So these are all focused around comparing the average rate of change to the derivative and finding the place where they coincide. In a sense, as we talked about in the very beginning of this lecture, what you're trying to do is find the place where the secant line is parallel to the tangent line, with that secant line found in a particular closed interval of the function. Now, of course, there's lots of requirements there, so we'll talk about those requirements as well while trying to give you the examples of solving this. And again, if this is one of those skills where you're struggling with or you're just not finishing problems, which is a really common mistake, know, 1, that you need to figure that out because it's on the standard quiz. 2, it's a hugely important theorem moving forward and something that's going to pop up all the time. And 3, when we do multiple choice questions around this, I'm going to have those mistake answers that you're looking for. So be on the lookout, I'm coming for you. So first and foremost, in order to use the mean value theorem, it's helpful to remember what the mean value theorem says. So basically, I'll write it out from memory. So first, if f is continuous for some closed interval, a to b, and differentiable, and again, I'm going to abbreviate differentiable for the sake of simplicity, and differentiable for that same interval but the open version, then there, and I want to use the symbols, but I'll be careful, then there exists a C in AB such that f of b minus f of a over b minus a equals f prime of c. So basically we're guaranteeing there's a place where the instantaneous rate of change, or the derivative, is equal to the average rate of change, or the slope of the secant line, on that interval. So basically there is the MVT, the mean value theorem. It's one that you do need to know the statement of, and that I will test you on knowing the statement of, so be prepared for that. But the nice thing is this also kind of gives us a roadmap of what we need to actually do to attack this. So first, the first thing that we need to do before we start to attempt any problem is we need to guarantee continuity and differentiability. So in here, the first thing I noticed with our first example, A, is that f is a polynomial. And again, I'm going to have to do a whole bunch of this, so I'm going to move pretty fast. But f is a polynomial, which means f is differentiable and continuous. So if you're in a multiple choice problem, this may not be something that you have to write out, but I think it's a good habit to get in. Just basically make sure that you're able to actually validly apply that theorem. So we're definitely good there. So that means that we're eligible to continue forward, which is all about figuring out these two pieces. So the first thing I usually do is I construct the average rate of change. That'll be f of 4 minus f of 1 all over 4 minus 1. We'll calculate out this thing. It's going to be 64 minus 24 minus 1 minus 6 all over 3. That's 40 minus a negative 5 all over 3, which should be equal to 15. Keep in mind, as we've said before too, that for the difference quotient, you do need a difference quotient, so why don't you just get in the habit of putting that? It's a good idea. Next, from there, we're going to calculate the derivative. So again, oftentimes the derivative isn't the hardest part, although obviously product rule, chain rule, quotient rule, all of them are possibilities here. In this case, it's the simplest derivative rules we could ask for. We get 3x squared minus 6. And then finally, our job is to bring those pieces together. So we want to figure out when does 3x squared minus 6 equal 15. So solving some stuff around, we'll get 3x squared equals 21. We'll get x squared equals 7. And we'll get that x equals negative root 7 and positive root 7. Now finally, before you box your answer and settle for an incorrect work, there's a mistake here. The mean value theorem guarantees values where the slope of the secant line and slope of the tangent line are the same, but those values that are guaranteed have to be in the interval on which we were applying the mean value theorem. So in other words here, as we look at those two answers, negative root 7 is not inside 1 to 4. So that means that value, while it does have the slope we're looking for, does not have the slope on the interval we're interested in. So that means that the only answer that we have here, the only value guaranteed by the mean value theorem, is positive square root of 7. And there is our first work. Now as a heads up, this is probably the most basic the question could be. Like seriously, this is probably the easiest it could get. But notice even in an easy problem, there were potential distractors because of the possibility of some values outside of the interval that we were interested in. So put that in the back of your brain as we move forward. Next, we're going to up the ante a little bit. We're going to look at 6b. Oops, sorry, tried to bold nothing. That's what I was looking for. So we're going to look at 6b. So there is the mean value theorem up in the corner. So as we start things off, remember the last time we guaranteed continuity and differentiability? Well, square root of this thing is going to be continuous and differentiable. And in this particular case, continuous, differentiable, that's going to be true for its whole domain, at least its whole domain except for the possible vertex point. So looking inside here, values that we can plug in are all the ones larger than negative 2 or larger than or equal to negative 2. So in our case, that's going to be for x greater than negative 2. And notice that we have 0 to 6, which means that we've chosen a good interval. So we're good to go. That means we're ready to actually do the computation. So this will be g of 6 minus g of 0 all over 6 minus 0. Solving some stuff, we're going to get the square root of 12 plus 4, the square root of 16, minus the square root of 4, all over 6. And that becomes 4 minus 2 over 6, which is 2/6 or 1/3. So there's our average rate of change. Next, we want our derivative. So in order to do g prime of x, we do need to use the chain rule. So hopefully you see that due to the 2x plus 4 on the inside, whose derivative is not 1. So in here, if we look at the ingredients, the derivative square root of stuff is 1 over 2 square root of stuff. And then we multiply by the derivative of the inside, which is the derivative of 2x plus 4. Now you probably recognize that derivative of 2x plus 4 as 2, which gets us, 2x plus 4. Those guys divide out. It means our derivative is 1 over the square root of 2x plus 4. And remember what we were trying to do is figure out when that derivative coincides with the average rate of change. So bringing this all together, we need to solve this equation. So looking at this equation, I'm going to go ahead and flip both sides of the equation because the numerators are the same, which means that we need to make the denominators equivalent. So we want to figure out when the square root of 2x plus 4 is equal to 3. I'm going to square both sides. That'll give me 2x plus 4 equals 9. That'll give me then 2x equals 5. And our one value is, theoretically, x equals 5/2. Now, of course, pause for a second, ask yourself, does 2.5 fall in the interval we are given? Yes, indeedy it does. 2.5 is definitely between 0 and 6. So we found our value. Another nice mean value theorem in there. The only big thing was that we did have to use the chain rule that time. So you can see the sort of wrinkles that get thrown in there. Most of the time just with the differentiation you have to do. Okay, our third example using the mean value theorem. Just kind of in a straightforward, like computational way. Kind of your level 1 questions, just kind of spiced up a little bit, is analyzing the function r of x, a rational function, x plus 1 over x. Now as I jump in here, the first couple problems we've done, we focused on differentiability and continuity first. Wanted to make sure that the function was differentiable and continuous as appropriate. When I look at r of x, though, oh geez, r of x has a vertical asymptote. And at first my mind's like, no, you don't get to play here no more, because unfortunately it doesn't seem to apply. The thing is, that vertical asymptote is wherever the denominator is equal to 0, which in our case occurs at x equals 0. But that is not inside our interval from 1/2 to 2. What that means is that we're perfectly fine. R is continuous and differentiable. And here, though, we can't just say R is continuous and differentiable. We should specify the interval we're talking about. So it's specifically differentiable and continuous on 1/2 to 2, the only interval we care about. So bullet dodged, we're in good shape still. From here, we start with our average rate of change. So in this case, it'll be r of 2 minus r of 1/2, all over 2 minus 1/2. And by the way, this one's kind of exciting. I wrote this one without actually checking my answer, so without doing the problem ahead of time, so we'll see if that burns me horribly or not. So as far as values here, if we plug in 2, we get 2 plus 1/2. Next we get 1/2 plus 1/2 plus 2. Interesting. Ooh, aggressive. So let's see, is that right? Did I do that right? If we put in 1/2, we get 1/2 plus 1 over 1/2, which is 1/2 plus 2. Yes, it is. This then becomes 3/2. Now in our numerator, I noticed that 2.5 minus 1/2 plus 2 is equal to 0. So this entire average rate of change is actually equal to 0, which is a really interesting result, but we're just going to set that aside for the moment. Instead, let's go and actually find the derivative. So in our case, we want r prime of x, taking the derivative of each part, or looking at this maybe a little bit more carefully. That's x plus x to the negative 1 power. Means our derivative is going to be 1 minus 1 over x squared. Now we want to figure out where this is equal to 0 in our case. And looking at this, you can probably already tell where it's going to be, but I'll play it safe. It means 1 has to equal 1 over x squared. That means x squared has to equal 1, and that means that x is equal to negative 1 or positive 1. Now being careful one more time, we had the same situation pop up earlier. We are looking at the interval from 1/2 to 2, which means that negative 1 does not apply because it's not in that interval. So our answer is x equals 1 only. So interestingly enough, not that it has to be something that you'll remember, but technically this was a situation that could have applied to Rolle's theorem. Rolle's theorem is the mean value theorem, but specifically when the endpoints are at the same height, and since our numerator zeroed out, that meant our two y values were at the exact same y value. So there you go, just something kind of neat to see. Turned out really nice. I feel like I dodged a bullet there as well, because it worked out really nicely. Okay, finally, we have question 6D. And other than using a piecewise function like we did in, I believe, question number 4, I'd say this is one of those problems that's going to be the most challenging, just because you've got a trig function. There's lots of strange things that can happen when we deal with trig functions. At this point, though, what I notice is that I've got the combination, or not a composition, a sum of two continuous and differentiable functions. So polynomials and sine curves. And that tells us that we have a continuous and differentiable function. So it's continuous and differentiable, so we're eligible to continue. So let's go ahead and do that. We won't dwell on that. So from here, we're going to have t of 1 minus t of negative 1 all over 1 minus a negative 1. Looking at our ingredients, when we plug in 1, we get 1 minus sine of pi. Then we'll have minus 1 minus sine of negative pi. So you can see there's going to be a little bit of crunchy trig in here for us to work with. So I'll be over 1 plus 1. Now in our numerator, I know sine of pi, like here we'll do a quick little drawing on the side, That's our unit circle. Sine of pi is 0, and sine of negative pi is the exact same sine of this, or is sine of the exact same angle. So that's going to be 0 as well, which means we really get 1 minus 0 minus negative 1 minus 0 all over 2. And simplifying things, that becomes 1 minus a negative 1, which is 2 over 2, or 1. So basically our average rate of change is 1, which is fairly clean coming out of a mess such as that one. But of course that's not the end of our process. We need to next find the derivative. So we'll compute t prime of x. The first term's derivative is just 1 because it's linear. So that's just a line with slope 1 and intercept 0. The derivative of sine of pi x, in this case we've got the chain rule due to the pi x. So that pi x requires us to use the chain rule. But it's an easy thing. The derivative of pi times x is just pi. So it'll be 1 minus pi cosine of pi x. We want to figure out where this thing is equal to 0. So, thinking I may have made a mistake here. But let's find out what happens. Let's just see. We'll answer it as best we can. So from here, if we're trying to solve this, that means we need to figure out, no, we don't have set it equal to 0. I figured it out. Never mind. Just ignore me. Okay, so that is our derivative. We've got our derivative. We want to figure out when is that equal to 1. So moving some stuff around, I'm hoping that you can quickly see that that's going to be equal to 1 at the point where pi cosine of pi x is equal to 0. Because imagine if 1 minus something equals 1, then that means that second thing would have to be 0. So we need to figure out when pi cosine of pi x is equal to 0. In other words, we need to figure out when cosine of pi x is equal to 0, because you can totally divide both sides by pi and not run into any problems. I'm doing some trig thinking here for a moment. Sorry. Still afraid of coughing. It's not that it hurts, it's just I'm afraid that the holes in my back are going to cause the disc to come out. Apologize. So cosine of pi x is 0 at pi over 2 and 3 pi over 2. So in looking at these pieces then, what I can say is that the argument has to be equal to pi over 2 or 3 pi over 2. Technically, I might also want to throw in there negative pi over 2 because of the fact that we're going from negative 1 to 1. So I'm going to put it in there just to be safe. Now when I get there, what I should do is I should multiply all sides by 1 over pi. In fact, I think I made a good call. We'll have x equals 1/2, 3/2, and negative 1/2. I mean, technically, if you want to go the other direction, you could get negative 3/2. But remember now, we were talking about a particular interval that we were interested in, that interval being negative 1 to 1. So that means that these two need not apply. But we do have two values that are guaranteed, negative 1/2 and 1/2. And again, that one turned out okay. But felt a little hairier. So you can kind of see, like, you get a good idea of the spectrum that we've been looking at here. There's kind of the super basic polynomial version. We have some versions involving chain rule or some weirdness to it. And then we have kind of the involved triggy version, in addition to, of course, the piecewise one we did in part 1. But there is a really good collection of mean value theorem problems. So hopefully that's kind of added some to your understanding and you feel pretty good about what you're seeing with using the mean value theorem. Okay, that next brings us to question number 7, the last problem on the first page, which is exciting for me, even if it's just the first page. So in here, in this situation, you're given a table, or a sign chart. Not even really a table, but a sign chart. And I'll point out to you that the sign chart you're looking at is for f double prime of x. So we're talking about f double prime values. In addition, you're told in the problem that 3 particular x values produce a derivative of 0. So given that information up the top, the first thing I'm going to point out is that we now know that f has 3 critical numbers. So those 3 critical numbers are x equals negative 4, 17 over 3, and 42. So keep that in the back of your mind as we start things off. Next, we're given a sign chart for f double prime. So in other words, we know stuff about the concavity, or about the sign of the second derivative of the function. Question is, how can we then find the x-coordinate of the relative extrema and classify them? Well, the trick here is that since we've got information about the second derivative, this is begging us for what we call the second derivative test. And the second derivative test is focused on using the concavity or a concavity at a critical number to determine whether or not you have a relative maximum or a relative minimum. The idea is, if you're at a critical number where the slope is 0 and your function is concave down, that tells you that you have a relative maximum. So conc down, relative max, but specifically conc down at a critical number. On the flip side, if we are concave up at a critical number, then we have a relative minimum or a local minimum because we're concave up. And something you'll notice is when I do these, I usually do draw a picture. So basically keep that in mind as well. So in order to do this, we're going to need to apply the second derivative test multiple times. So let's do that. So let's start with x equals 4. So at x equals -4. So the first thing I need to do is figure out what interval I'm in, and I see that -4 is going to fall right in here. Down there, what I see is the second derivative is negative. So if we've got a negative second derivative, that means our function is going to open up like so, which tells me we have a relative maximum. So at x equals 4, we have a local max. And then our reason is because f prime of -4 equals 0. So in other words, we're at a critical number. And f double prime of -4 is less than 0. So in other words, f is concave down at a critical number, which gives us a local maximum using the second derivative test. So there's our first one. Okay, same strategy for the second one. Got 17/3, that's 5 2/3. So 5 2/3 is positive. It's going to be somewhere between this guy, which is 16.5. So 5 2/3 will fall right here. So 17/3. So down here I notice that we have positive concavity, which means our graph is concave up at that critical number. So we can say for that one, at x equals 17/3, we have a local minimum. And our reason would be because f prime of 17/3 is equal to 0, and f double prime of 17/3 is positive. So once again, we're applying the second derivative test. Last but not least, I wish this one wasn't even here because it seems like it's beating a dead horse. It's the exact same process. The last one is 42. 42 clearly falls over here. 42 has positive concavity. So what I'm going to do is sue me for doing this. Don't sue me. I don't have a lot of money. I'm going to use up all my sick leave here. So what I'm going to do is I'm just going to change one thing. I'm going to change it so that this says, instead of 17/3, it says that x equals 42. There's a local minimum. The reason being we are concave up at another critical number, which means, of course, that we have a local minimum by the second derivative test. So again, this was all focused on the second derivative test, asking it in an interesting way. And in fact, you'll see one more interesting way that pops up later on, because for some reason I didn't have enough second derivative test stuff here. This next brings us to the second page of the review, question number 8. I'm very happy to be on the second page and starting to move forward, although lots of questions still remain. In fact, looking at that countdown there at 24 out of 62, remind me not to bend down. I'm not allowed to do that. Okay, in question number 8, it says the table at right gives values of the twice differentiable function g of x. Based on the contents of the table, is the graph of g concave up or concave down? Why? So here's our thing. We want to figure out what's happening right there. So to help me, I'm just going to copy the table one more time. I'm going to make it larger. So basically, this is a common question type. It's an opportunity to see if you know how to... actually, there's some mean value theorem used in here, although in reality, it's a simpler thing than that. It's using one of the properties that defines concave up or concave down, which is determining whether or not your first derivative is increasing or decreasing. So here's my process. What I'm going to do is I'm going to estimate and find an average rate of change. And what that will do is it'll give us some approximate values of the derivative. It'll give us particular values that the mean value theorem would guarantee exist somewhere on that interval. And then we'll try to reason from there. Here's my thought. So right here, what I'm going to do is I'm going to compute the average rate of change. That'll be 8 minus 14 over 2 minus 1, which is equal to -6. And in fact, just for the moment, I'm going to go this way, put it a little bit further over. So there's my first one. My second one, following the same process. The second interval we can look at, our average rate of change is going to be 3 minus 8 over 3 minus 2, which is equal to negative 5. Last but not least, if we look here, average rate of change is going to be negative 1 minus 3 over 4 minus 3, which is equal to negative 4. So what I've just done is I've calculated 3 average rates of change, but recall, when using the mean value theorem, those average rates of change have to be equal to the derivative somewhere on that interval. So basically we found 3 representative values of the derivative for this function g of x. Now looking at these values, what I notice is as we move from one to the other, we're going up each time. What that tells me is that our first derivative, g prime of x, is increasing. Basically, values of the derivative are getting bigger and bigger. If g prime of x is increasing, that's completely equivalent to saying that g double prime of x is positive. Because, of course, g double prime of x is the derivative of the first derivative. So if g double prime is positive, that tells us that g is concave up. So that would be my expectation. And again, for our reason why, I think you see it. What we did was we found a couple of values of the derivative that are guaranteed to be there by the mean value theorem. Then we were able to recognize that because of those values, that tells us that g prime seems to be increasing. And if g prime seems to be increasing, that's code for saying g is concave up, which is just one of our properties. So again, even though this looks like a pretty involved question, it feels like it comes out of nowhere, you can work through it pretty fast. Beyond this approach that I just used, the only other approach that I've seen has been for students that attempt to sketch this out. And I mean, there's some danger in doing this. I know 1, 2, 3, 4, 7, 8, 9, 10, 11, 12. Okay, so basically if I test this out, I'm just going to see if this works, because unfortunately I know there's some limitations here using this method, but sometimes people are successful. Get 114, 2, 8, 3, 3, and 4, what do we have? 4, negative 1. Let's see if I did that right. Down. So somewhere down here, I'd say. So if we were to imagine what this looks like, I mean, yeah, it does look like it's slightly concave up, but the difficulty here was the closeness of the points meant that it was kind of hard to see for sure. If we do our scale a little poorly, it might not have looked as nice. So basically, you could also try to draw a picture, particularly if the values are far more spread apart. Like if we had 140, 80, 30, and negative 10, you'd probably be able to do it a little bit better. For the moment, I'd say that the drawing the picture isn't quite as accurate as what we did here otherwise. The next question that we hit is actually one addressing a familiar concept. In question number 9, you're given information about the second derivative. In this case, our second derivative is provided as a graph right here. So this function is h double prime of x. Like that's what we're looking at here. It then says if h prime of 2 is equal to 0. So h prime of 2 equals 0. Well, that tells me right off the bat that x equals 2 is a critical number of h. So that's an important piece as well. So x equals 2 is a critical number. Our question asks us, does h have a relative maximum, relative minimum, or neither at that point? Well, to answer that question, all we need to do is apply the second derivative test, since what we're looking at here is the second derivative. So again, we're thinking second derivative test because we're looking at the second derivative. So the second derivative test says, basically you can use the sign of h double prime. If h double prime is positive, or h double prime of the critical number is positive, then of course that means we're looking at a concave up situation, which means that we have a local minimum. On the flip side, if the second derivative is negative, that means that we have a local maximum. So to finish this particular point off, what we need to figure out is what is h double prime of 2. So in looking at our picture, since this is 1 and this is 4, that means 2 falls somewhere in here. And although we can't be sure the specific value of h double prime of 2, what that one hurt. What we can tell is that h double prime of 2 is definitely negative. What that tells us is that h is concave down at that point. So what we've just shown is that we are concave down at a critical number. And what that tells me is that we have a maximum. So to conclude this thing, we could say that there is a relative maximum specifically as a relative maximum on h of x at x equals 2, and our reason is because h prime of 2 equals 0 and h double prime of 2 is less than 0. So we are concave down at a critical number, which means that we have a maximum by the second derivative test. So again, this goes really well with that table from earlier, just a different presentation style for what we had before. Next question is question number 10, with this terrible printing up on my page, but whatever, here's is fixed. So in question 10, we are asked to explain why the mean value theorem can't be applied to the function p, given p of x equals that piecewise function. So as far as pieces here, we've dealt with the mean value theorem earlier. The things that are required, though, that you might have in your mind, is we need to be continuous on the closed interval, and we need to be differentiable on the open interval. Now what's interesting in this problem, and probably is an oversight on my part because I made up this question, is that we're not given any interval in this problem. So specifically what that's kind of telling you is that we've got to find a reason why we can't apply the mean value theorem on any full interval here. That basically we've got to be careful with the mean value theorem. If I could go back, I'd probably say something like, why can't we apply it on negative 42 to 42, or something along those lines. But setting that aside, since it's not here, just know that this question wasn't asked perfectly, but the concept itself is accurate. We're trying to check if these two properties hold. So now, in order to check if those two properties hold, we need to go back to some work we've done before. We need to check if this function is continuous and differentiable. So first, we're going to need to check about continuity. Now, in looking at our function, we have a polynomial for the first branch and a polynomial for the second branch. What that tells me is that each branch is inherently continuous and, in fact, differentiable. Polynomials have that beautiful property. The only place that interests us is the boundary. So what we're going to investigate first is whether or not we have a continuous function that is continuous at the boundary x equals 2. So again, we've done this many times before. We'll check the left-hand limit of p, and we'll check to see if it's equal to, actually I'll do it separately, the right-hand limit at 2 of p of x, and we'll question whether or not these two things are equal. So to do that, let's see, let's plug in 2. We'll get 3 times 2 squared minus 4 times 2. Our question is, does that equal 2 cubed minus 4? We're going to have 12 minus 8. Over here we're going to have 8 minus 4, and I can already tell both of those are 4. What that tells us is that we have enough to conclude that this function is continuous. Continuous at x equals 2. And that means that we can apply, as of this moment it would seem, the mean value theorem on any interval, even those containing the boundary. Except there's one other possibility that we need to check for. We might have this part taken care of, but our question left is, can we take care of differentiability? So in other words, for our second one, we don't want to look at p continuity, we want to look at p prime's continuity. So it would help to first calculate out what p prime of x is equal to. It's going to be 6x minus 4 when x is less than or equal to 2, and it'll be 3x squared when x is greater than 2. So for the second one, we want to check the left-hand limit as x approaches 2 of p prime of x. We want to see if that equals the right-hand limit as x approaches 2 of p prime of x, because we want to make sure that there's not a sharp turn at x equals 2, because if there was, that would be non-differentiable. We could not apply the mean value theorem. So, dang, need to go get water after this. So looking at those limits, we're going to have 6 times 2 minus 4. We're checking to see if that's equal to 3 times 2 squared. So it's an open question. We'll have 12 minus 4 is 8. Our question is, does 8 equal 12? Unfortunately, 8 does not equal 12. That means that, of course, p prime is not continuous. What we just showed is that p prime has a jump at x equals 2. But more importantly, that means that p has a sharp turn. And specifically, that sharp turn is at x equals 2, which implies that p is not differentiable. And specifically, it's not differentiable on any interval containing x equals 2. So again, I'll probably go back and fix this question so it looks like this, but for the moment, here's a sharp turn at x equals 2, so p is not differentiable. which means we can't apply the MVT. So again, it's one of those little things. We dealt with differentiability in the past. I'd say one of the biggest reasons isn't just because it's a cool property and a property we should be aware of, but because it affects whether or not we can apply the mean value theorem. So here we saw a situation where an otherwise continuous function has what we call a sharp turn. Actually, it's sharp like that. It's positive and positive. And because of that sharp turn, we can't apply the mean value theorem. Okay, the next question we're going to look at is question number 11. Question number 11 asks us, on which intervals can the extreme value theorem be applied to f of x equals this function? And of course, this function is rational, which means that we have some potential issues to think about. So before we start jumping in here, I like that this question doesn't ask me to explain, so I'll just try to do it verbally as I check each one. Remember that the extreme value theorem basically says if f is continuous, and specifically f is continuous on a closed interval a to b, then f has a maximum, I'll just say f has max and min values on that same interval. And of course I keep it as a closed interval because the endpoints themselves could qualify. So in looking here, we want to consider each of these intervals and look to see if we can apply the extreme value theorem. And like I said, I want to move through this pretty quickly because this isn't my favorite question to look at. So as far as pieces here, first thing to look at is we've got our function f of x. So f of x is 2x minus 1 over that denominator. And if I factor that denominator, I see x minus 4, x minus 6. Yeah, I do it pretty fast. It's okay. So what that tells me is that f has two vertical asymptotes. And specifically, those vertical asymptotes are at x equals 4 and x equals 6. So the reason this was such an essential place to start is that this tells us the places where f is not continuous. So basically, we have to look for any intervals that contain 4 and 6 because the presence of the vertical asymptote will disqualify us from using the extreme value theorem. So looking at some pieces here, some things that I can see, automatically, I'm going to say no to b. And our reason is b contains the vertical asymptote at x equals 4. So basically b is gone for sure. So out of there. In addition, c is gone as well. The reason c is gone is because it's an open interval. And in fact, just picturing what an open interval can look like, imagine that our function on 1 to 3 looked something like this. The maximum value and the minimum values would not be included. It would have what is in real analysis called the lim supremum and a lim infinum, but those two things are not actually endpoints that are included in our interval. So there is no maximum or minimum value. That's why the extreme value theorem requires continuity on a closed interval, so that way we can use those 2 points. As far as intervals that will work, for sure D is going to work. It's continuous, and it's closed. And also, in the same way, it will also work for A, because once again, the function is continuous there, on the account of neither x equals 4 nor x equals 6 is included, and our interval is closed. That leaves us one last thing to check out and to consider here. That last one for us to look at is 6 to 10. Basically, this one is automatically disqualified because of the fact that this function is open. This interval is an open interval. So by using an open interval, unfortunately, it disqualifies us. And in this case, because we're actually having one part of the interval at that vertical asymptote, like you can kind of picture what's happening here. We have something that looks a little bit like this. We're trying to find the maximum value from here to there. But unfortunately there, we're going straight down to negative infinity. So basically, E is out as well. That means the only 2 intervals that I applied were A and D. There we go. Okay, the final piece of page 2 of this review, this massive review I wrote. So in here, looking at this, we've got a bunch of description in here, and I think 5 questions to look at involving a visual depiction of a function. I think that's what it says. So the graph of function f of x is shown at right. So yes, we are looking at the function f of x. So this is f of x. Let's see what else we know. It says f has a jump at 1. That seems reasonable. I agree. There's a sharp turn at 2. That looks like a sharp turn to me as well, so I'll accept that. And it says there are relative extrema at -3 and x equals 1. So basically those two as well. It says it's also known that f is linear for x greater than 2. So that means that this thing over here is a line, and I'm going to go ahead and say that, yeah, that looks reasonable. It looks like a line to me too. They're not lying. So from here, we're supposed to use this to answer the questions. So next thing. So looking at our first question, can the extreme value theorem be applied to f on 0 to 3? So in other words, we're looking at the closed interval from here to here. Well, unfortunately, the jump's in the middle. So unfortunately, the answer here is no. F has a jump, turn, 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 turn. Notice it literally says there's a jump at x equals 1. Since there's a jump at x equals 1, which is in the interval from 0 to 3, what that means is that f is not continuous on our interval, and that means, in addition, that we cannot apply the extreme value theorem, which is extremely disappointing. Nope. We can't apply the extreme value theorem. So now what's kind of interesting about this, though, I don't know if anyone is noticing this, but if we looked at it, the interesting thing is you might think that that's a mistake, because there is a maximum value on this interval, and there is a minimum value. And yes, I cannot disagree with you. There are absolute maximum and absolute minimum values on the interval of 0 to 3, but the problem is they're not guaranteed by the extreme value theorem. It's just kind of a happy coincidence that it happens to work out in such a way that we can actually get those values. So don't be confused with the fact that there is something there with the fact that the EVT can actually be applied. What matters for the EVT is if you have continuity and a closed interval. In this case, by failing continuity, we just can't apply the EVT, even if there might be places there. Okay, 12b, find the absolute maximum value of f for -3 to 5. Now, once again, this is kind of a slight variation on what we just talked about on the previous one. So in the last one, we talked about how the extreme value theorem didn't guarantee a maximum value on the interval from 0 to 3, and 0 to 3 is definitely contained from -3 to 5, which is way the heck up here, so we're going to have to play with that in a second. Now, with that in mind, just know that even though we aren't guaranteed one by the extreme value theorem, of course there can be one. We talked about how even on the previous page, there was one. In this case, though, what we have to do is we need to actually just kind of proceed through and see if we can find the highest or lowest points. So now in this case, we ask for the absolute maximum value of f, and at first you might think the absolute maximum value occurs right at that relative maximum, at x equals -1, which gives us a value of, it appears, 5. But actually, that would be incorrect. The reason is, over here, we've got some massively high value that's being attained over there. So if we want the single largest value on there, we're actually going to find out that that occurs at f of 5. So what we're looking for is f of 5. So in other words, that's what we're going to set it like 5 times. That's what we want, is f of 5. So to get there, we need to figure out what f of x is in that region. So for x greater than 2, we said that f was linear. And as far as our pieces there, we can write the equation. I'll use this point as my x1, y1. It'll be y minus 0 equals, now for our slope, we're going up 1, 2, 3, 4 over 1. So it's going to be y minus 0 equals 4x minus 3. That means our equation is 4x minus 12. And from there, if we take those two ingredients into account, we want to figure out f of 5. So f of 5 is going to be 4 times 5 minus 12, which is 20 minus 12, which is 8. Now remember, we did have in our grasp a value at 5, which was a candidate for the highest value. It was at a critical number, in fact, so calling it a candidate was pretty accurate. But of course, 8 is greater than the 5 that we kind of had in our hand already, which means the absolute maximum value, also called the global maximum value, global max value, is actually going to be 8. So again, what I like about that question is that it asks you to really think about things and use your ability to reason with a graph and even reason linearly in order to solve the equation or solve the problem. Hey, question C. What are the critical numbers of f of x? Provide a reason for each answer. I really don't want to provide a reason. Don't make me give a reason. I don't want to. We'll see what happens. Tired. I'm actually really sore. I probably need to rest after this. So, the graph of critical numbers. So first of all, a couple things to note. First, critical numbers occur, sorry, I said that wrong. Excuse me. Local extrema happen. So yeah, it's not a surprise. Local extrema happen. Yeah, they do. They do sometimes happen. Local extrema happen only at critical numbers. So that's a really important first thing to point out. So any relative extrema we have for this function is going to be a critical number for that function. So that tells me right off the bat that I've got 3. I've got 1 right there, 1 right there, and I've got 1 right there. So basically right off the bat we have 3 critical numbers. Those critical numbers of f include, it looks like x equals -3, x equals -1, and x equals 2. Now note x equals 2 is a sharp turn, so it's a place where the derivative does not exist, but of course the point's clearly there, so we include it. Now if you put those 3, I'd say you did a nice job, but there's actually a 4th one in here. That 4th critical number actually occurs at x equals 1. The reason x equals 1 qualifies, oh shoot, I circled it fast, sorry. Our last one is that x equals 1. The reason x equals 1 qualifies is that the derivative does not exist at that point. So in fact, I could probably even say that. Down here, f prime of x does not exist. So basically, and in this case, it might feel weird. You might want to say that, well, it's not fair. You can't call x equals 1 a critical number because 1 isn't in the domain of f. But actually, 1 is in the domain of f. Look at that. At x equals 1, y equals -3. That means the function is defined there. There is a value, so 1 is in the domain of the function, so it qualifies as a critical number as well. So from there, basically putting out our reason, f has relative extrema. So there is our work. I'm going to just stop right there. Again, this is one of those like trickier questions. It almost feels like a visual true or false question. It's the kind of thing where I'd ask, does f of x have a critical number at x equals 1? And your job would be to reason through the idea of what it means to be a critical number, how it has to be in the domain, all that good stuff. But again, works pretty well. I think it's a pretty good question for something original to come up with. Okay, next that brings us to D. Is there a point of inflection on -3 to 1? And I believe I actually asked this question on the 2017 AB class, Unit 3 exam. It might be off by 1 year. It might be 2018. I don't remember for sure. But in looking at here, we want to know if there's a point of inflection. So now when you hear POI, there's so many different definitions that might come up into your mind. You could think of f double prime changes signs. That's definitely one possibility. You could see f double prime changes between increasing and decreasing. That's one that we use most often when we're dealing with derivative analysis graphs and stuff like that. But then there's actually one more thing that would define a point of inflection. And we don't use it very often because we're usually reasoning through using the derivative or the second derivative. But actually you also have a point of inflection at a point where f changes concavity. In reality, that's almost the most basic definition of a point of inflection. It's a place where the concavity changes. You know, we try to draw a function, we draw something like that. We can see that there's got to be a point of inflection down there because our function was concave down, and then our function became concave up. So given that in your mind, if we want to look at the interval from -3 to 1, which by the way occurs from right here to here, what we need is we need to see evidence of one of those 3 things. And since we're looking at the graph of f of x, I think it's easiest to look at f's concavity. So in looking here, the first thing I see is that since we're starting at a relative minimum, that means that we are concave up at first. So we are concave up for sure. Then, from there, we go concave down at the relative maximum that occurs right here. So basically what that tells me is our function has to change from concave up to concave down, somewhere on the interval, from -3 to 1. Therefore, there must be 1 in there. So as far as crafting an actual argument here, of course this is the least fun part. I love thinking about it. I hate trying to describe it out. So here's what I see. F of x has a relative minimum. I'm just going to call it rel min. Hope that's okay with you. If it's not, well, fight me. You can't find me. I'm stuck at home. a relative minimum at x equals negative 3. So f double prime of negative 3 is less than 0. And second, f has a relative max and we said it was at x equals negative 1, right? Yeah, x equals negative 1. So f double prime of negative 1 is positive. Or sorry, did I flip those? I think I did. I flipped the signs. I apologize. It's supposed to be greater than, it's supposed to be less than. So basically for the first one we're concave up, so f double prime of negative 1 is positive, second one is negative. What that tells us then is thus f changes from concave up to concave down on negative 3 to 1. So f has a POI at, and we'll be real formal here, x equals c for negative 3 less than c less than 1. And truthfully, there's probably also some sort of intermediate value theorem argument that you could make, talking about the second derivative having to be 0 based on those two things. But remember, we aren't guaranteed that this is a twice differentiable function, so I think it's easier to appeal to what we have, which is clearly the presence of a relative minimum and a relative maximum at each of those two corresponding points, for which we know the concavity is completely set. So again, I'd say that's a pretty tough question. If I were to ask you this on an exam like I did on that old exam, whenever it was, I would not ask you to explain it because that's really difficult and hard to kind of get your words right for, even though I'd like to think that people could think their way through it. I'd probably ask you as a multiple choice, like, is there one on there, true or false? Something like that. Okay, that brings us to the final question on page 2. Heck yes, I'm excited. Are you excited? So on here, you're asked to evaluate the limit as x goes to infinity of 5x plus 7 over f of x. Truthfully, this is not unit 3. Like, let's just be clear for a second. This is not unit 3. This is literally directly off your unit 1 test. In fact, it was the final regular question that didn't involve pride or drawing some sort of chimera beast problem that might be talking like Max and saying, give me hugs. So, in this particular case, what we're trying to do is I'm just trying to test you to see if you can still do this. I think it belongs in this type of question. I think it's a good thing to throw in there. So now, the tough thing here is as you look at this, remember the important thing is to look at, in this valuation of a limit as x goes to infinity, is to see what the ratio is doing. Well, in here, as x goes to infinity, f of x is linear. And in particular, I think we already found this. I think it's f of x equals 4x minus 12. Quick check says, yeah, 4x minus 12. So basically, that's what f of x is as x goes to infinity. It's this line over here. So given that information, that means what we're trying to evaluate is the limit as x goes to infinity of 5x plus 7 over 4x minus 12. And now if you go to attack this thing, of course I'm hoping you could see the answer right off the bat, but if you can't, remember that we can kind of do our own special infinity trimming the quills technique. We can nerf the leading terms. I think that was the way we described it in class. We can nerf the leading terms by multiplying by 1 over that degree term. In this case, we'll rewrite our limit in a completely equivalent but cosmetically different form. Get the limit as x goes to infinity of 5 plus 7 over x over 4 minus 12 over x. When we direct sub then, we get 5 plus 7 over infinity over 4 minus 12 over infinity, and a number divided by infinity is 0, which means our answer is 5/4. Now again, this is not a direct Unit 3 topic, but then again, I did say at some point in the future I might assess you on this and be able to give you some credit for it. So, excuse me, maybe this will be that opportunity. Never know. With that said, this next brings us to question number 13, the first question on page 3 of the review. Now, of course, as I look over at that third page, question number 14 looks particularly daunting, but let's not get ahead of ourselves. Let's take this one problem at a time. And that means we're going to start with question 13, which asks us to find the critical numbers of g of x. Now, of course, in this particular question, we've done lots of work with critical numbers here, so I don't think that's going to be the whole challenge, although there might be some twist to it. The real challenge is, of course, differentiating a product of binomial powers. This is one of our techniques and types of functions that we ran into, which involved both the chain rule, because of the fact that we've got that 2x minus 5 in there, and in addition, required us to use the product rule, as well as, of course, the power rule and scalar rules, all that good stuff. So we've got a combination and advanced differentiation skill that we need to use, so let's go ahead and start to attack it. Of course, knowing that we're going to be looking for places where g prime of x equals 0 or undefined, which is the definition of critical numbers. Okay, so in here, when we go take the derivative, these are pretty easy functions to differentiate, but I'll be super careful as we go through. We take the derivative with respect to x of 2x minus 5 to the 6th, and then multiply that times x plus 1 to the negative 4th. Then we're going to add to that 2x minus 5 to the 6th times the derivative of x plus 1 to the negative 4th. So going to differentiate these things, remember what we can do is we can think about bringing down the power and then the derivative of the inside. So for instance, if I look at this first one, we're going to bring down a 6, and the derivative of the inside is 2. That means our coefficient for the first one is going to be 12, and it'll be 12 times 2x minus 5 to the 5th. Once again, of course, times x plus 1 to the negative 4th. After that, we will have 2x plus 5, or minus 5 to the 6th. Oops. We will have, I should do it this way. We'll have 2x minus 5 to the 6th. But then we're taking the derivative of x plus 1 to the negative 4th, which means we're going to bring down a negative 4, and we'll have x plus 1 to the negative 4 minus 1, or negative 5. So there's our derivative. Of course, this is great. It's a huge start. We used the chain rule and product rule both at the same time. Good job, us. But what we haven't done is we haven't done anything that gets us closer to those critical numbers. We need to figure out where this function's derivative is 0 or undefined. So in order to do that, we need to start to pull out GCFs. So again, I'll go one piece at a time. I've got numeric GCFs of 12 and 4. That's going to pull out a GCF of 4. We've got GCFs for the 2x minus 5 family. The smaller power is 5. There are 5 of them and 6 of them. We pull out the smaller power, which is 2x minus 5 to the 5th. And then third, we've got the x plus 1 family. Oops, sorry. I forgot to mark the other one. Let me do that right now. So then we've got the x plus 1 family, negative 4 and negative 5. The smaller one is actually negative 5. So we're going to pull out x plus 1 to the negative 5. And then that'll leave us with whatever the leftovers are. So that'll be, in fact, 3. It looks like x plus 1 to the first. Then on the second one, it'll be minus 1. And it'll be 2x minus 5. So there's our stuff. To get our last critical number, we need to distribute these pieces in. This one will be 3x plus 3. Oops, terrible. It's 3 minus 2x minus a negative 5. So when we pull that together, we get our last one as x plus 8. So if we combine all this stuff together, we'll have x plus 8 times the other ingredients over here. Oh, come on, really? Is that how we're going to play? Come on, have I not been faithful to you? Jeez. Okay, whatever. Thanks for nothing. Okay, there we go. So there is our derivative. This is the glorious g prime of x. Of course, that wasn't our whole problem. Our problem involved finding the critical numbers. So naturally, what most people do at this point to find their critical numbers is they just go through and they say, okay, our critical numbers are easy. Let's just write down all the zeros. We have x equals 5 halves. We have oh, I didn't lay down. It's my fault. X equals negative 1. And last but not least, x equals negative 8. And then they just kind of box that. So there is one small problem, though. If that was your answer, you would actually be incorrect. Not for bad thinking necessarily, but for misunderstanding the definition of a critical number. So up in here, I submit one of those critical numbers as an imposter. The reason is g prime of x has to equal 0 or undefined, but it has to be true with g of x existing. So in other words, remember, we have to actually be at a point on the original function. In fact, in some textbooks, they don't call them critical numbers. They talk about finding the critical points, those x and y coordinate combos, where we have a potential relative maximum or minimum. So now looking up at our original function, we can see immediately that one of these critical numbers just does not actually fit in. That number is the one that has x plus 1 to the negative 4th and makes it equal to 0. Specifically, x equals negative 1 does not apply. The reason is g has a vertical asymptote at x equals negative 1. And because of that vertical asymptote, it is not a critical number, so our answer is actually just negative 8 and 5 halves. So it gets a little tricky, because of course if you were doing a sign chart here, you'd still need to include x equals -1. In fact, it's so tricky, I was messed up with this. I've had this wrong since high school, till last year and Mrs. Formaker corrected me on it. But at the same time, it's important that you know the difference. Still an important value, but it's not what we define as a critical value, which has to be actually in the domain of the original function, in our case, g of x. So there's 13. There was the calm before the storm. That will be question 14. Okay, bringing us on to question number 14. And I'm probably going to move through this a little faster than I'd like to, but I keep saying that, and then all of a sudden there's 60 minutes of video. I need to lay down this, so I need to move a little faster. So here we go. So in 14, what do we have? It says the graph at below. There's going to be someone out there going to be very offended by that. The graph below. We'll deal with that later. The graph below shows the derivative function f prime of x for some twice differentiable function f. So we know f is twice differentiable. So in other words, f prime should be differentiable and continuous as well as would it be f. It also says graph of f has horizontal tangents at -5, -4, -2, 1, 3, and 5. So that was pretty reasonable. I like it. We're supposed to use the graph to answer the questions. So the first question, we are supposed to find the critical numbers of f. Well, in this case, it says f is differentiable, which tells us, and again, this isn't something I normally write, it's just something I probably think, that tells us that f prime is continuous. And because of that, since f prime is continuous, it's defined everywhere. That means all we're looking for are the values of x where f prime of x equals 0. So we want the places where f prime of x equals 0. Keep in mind, this is not f, but f prime of x. So if we want f prime of x to equal 0, we want all the zeros of the derivative function. So in this case, there are actually going to be 4 such zeros. It looks like those numbers will be x equals -6, x equals 0, x equals 2, and 3, 4, 5, and x equals 5. And in there, that is our answer. We found the critical numbers. Our reason was right up here, but it didn't specifically ask us for the reason, so I think having it listed up there was probably perfectly fine. I'm your person that's going to grade your test, so it was perfectly fine. Okay, question B. Does f have a relative maximum, relative minimum, or neither at x equals 5? So we're looking right over here. Looking at our graph, what I see is f prime does not change signs there. In fact, notice on the left of 5, f prime is positive, and on the right of 5, f prime is positive. So f prime does not change signs. So f prime does not change signs at x equals 5. So f has neither. And technically neither what? Neither a frog nor a toad. We should probably say neither a local max nor min at x equals 5. And what you'll notice here is that in my explanation, I didn't write it in the traditional sense. I didn't say f has neither because, although that's obviously a great way to do it. In this case, I was thinking about what was happening on the graph, so I wrote down what would amount as the reason. In this case, f prime not changing signs. And then I said, therefore, f has neither a local max nor a local min. So there is question B. This is a pretty basic question. It's a pretty common question as well. But look out for those bounces in the first derivative, or even bounces in the second derivative, because that would include or suggest there's no point of inflection either. But I'm getting ahead of myself. Question C. On what interval is f strictly increasing? So f is strictly increasing means that f prime is strictly positive. So in a sense, maybe I'll write this one backwards. We'll say, right off the bat, we're going to state our intervals, and it's going to be true because f prime of x is greater than 0. Now remember, if there was no strictly, we'd be able to put the or equal to. But since it is strictly, we want to say greater than 0. So from here, looking at our pieces, we want f prime of x to be greater than or equal to 0, keeping in mind that we're looking at a graph of f prime of x. So greater than 0 is all the stuff that is above the x-axis. Above x-axis. So in looking, that's going to occur from here. This is terrible shading and it's shaking the computer or whatever. Here to here. So it's going to be f is strictly increasing. You can tell I really want to never do this review again. That's why I'm going into enough depth to write the phrase strictly increasing. So f is strictly increasing for, I'm going to start with -6 less than x less than 0. And, actually I'll list out all these intervals. Where else is it? It's above the x-axis here. Sorry. That would be from 2 to 5. And then last but not least, looking at our picture, it looks like it's also true for all the values of x greater than 5. And then our reason is because f prime of x is greater than 0. So again, if you were boxing it, I would say that you could probably box that part of the answer, but the justification is just as important and has to be there in order to get you the credit you deserve, or the credit that you want. I don't know if you deserve it, that'll depend on your answer. By the way, too, let me remind you, don't say it. If you say it, you owe Stephen King money. It is a clown movie. F prime of x is the function we're using to analyze. Be very specific. Don't call it the slope. Don't call it. Don't call it the function. Don't call it the graph. Call it f prime of x. Please. Por favor. Okay, that's 14D. At what x values does f have a relative minimum? Well, once again, I'm going to think about what that means first. So f having a relative minima look like this. If I just kind of think of it as me kind of reasoning up here. That means that we want f prime, or f, to go from decreasing to increasing. That's the same as saying we want f prime to go from negative to positive. So there's our thought. We're looking for negative to positive. So down here, I'll go ahead and write that. We'll say that the reason it has a relative minimum is because f prime of x changes signs. And it changes signs in such a way that f prime moves from, we said, negative to positive. And in fact, as far as the rest of us, let's see what we got. So negative to positive. So looking down here, we have negative f prime below the x-axis, positive f prime above. The first one I see is right there at -6. It goes from negative to positive. So we can say that there's one such value at x equals -6. Next candidate is x equals 0. Unfortunately, we go from positive to negative, so that's not a relative minimum. That's what? It's correct, it's a relative maximum. The next one I see, negative to positive. So at x equals -6, x equals 2. And then our next candidate is any other 0. Well, right there, we see that it goes from positive to positive. And since f prime goes from positive to positive, it's not there either. So what I can do is I can be a little bit better here and say that it has those relative extrema, or relative minima, at x equals -6 and x equals 2. That's just a terrible box. We'll say that. And our reason was already provided, because f prime of x changes signs. So if you recall, this is called the first derivative test we're applying. We just don't usually use the name first derivative test. We try to use the techniques that were provided, which is talking about the specific sign change pattern that we see at particular critical numbers. There is 14D. And here is 14E. So it wants us to find the interval on which f is simultaneously concave up and decreasing, with us justifying our answer. Well, to start things off, I'm going to begin like I did before. We're going to talk about the reasons. Like, what properties are we looking for that involve f prime of x? So in this case, we want f prime to be concave up, or we want f to be concave up. That means that we need f double prime to be positive, but more specifically, we need f prime to be increasing. Likewise, if we want f to be decreasing, we need f prime to be greater than or equal to 0. Oops, sorry, not greater than or equal to, less than or equal to 0. So basically, those are the two possibilities that we're looking for. I'm going to say this is true because f prime is both increasing and negative. I'm saying negative because there we go, and negative. I should probably say both concave up and strictly decreasing, but we'll forgive that for the moment. I don't want to go rewrite it. So those are the reasons. We're now looking for those places. So we want first f prime to be negative. So first and foremost, if we want f prime negative, that's going to be all the stuff down below. So the nice thing here is there are only two sections of the graph for us to look at, right there and right there. Beyond that, we've got to look at all our stuff. So we want f prime to be increasing. which means on this first little bit, f prime is definitely increasing. So we can say that this is true for x values less than -6. And actually, you know what? It says decreasing here. I'm going to include the or equal to in this case. So I just think it's better to say it that way. So I'll revise my explanation in a second. So there we have f prime is increasing and negative. Technically it should be non-positive, or non-positive, but whatever. Then from here we look at the next region right there. We are decreasing, so that doesn't apply. But when we go from 1 up to 2, f prime is definitely increasing. So what we'll say is that's true for, let's see, and we'll go from 1 to x to 2. We should definitely include the 2 because it was definitely decreasing. And as far as like at that point, I'm not going to clarify, I would accept that as well. So basically in here, what you're kind of looking at is I'm just kind of navigating the fact that I did not say strictly decreasing. That was a mistake on my part. I should have just said strictly decreasing. But for the moment, this is what I'm looking for. I'll be very careful on your exam as we go through. So in a sense, we should say strictly decreasing here, just to be safe. And if we said that, then we wouldn't have to deal with the or equal to's. So just know that that would be gone, and my explanation would be perfect. As of right now, it's a little bit fuzzy, but I'm going to let that go. Sad thing is I'm going to tell you for sure that a question like this will be either on your test or your final or both. Or, I don't know, every question you face for the rest of your life. So it's just a really good, efficient way to ask multiple pieces. There's how we find there, though. Again, we're using properties. We're talking about the definition of concave up using the tool f prime that we were provided. Okay, next, that brings us to question 14f. Am I close? I'm halfway. How many points of inflection does f have? Well, basically, we have POIs when, and I'll say because it's usually a reason, or how do you know? Because f prime changes. Now, of course, we'd normally say there's a point of inflection where f changes concavity, or f double prime changes signs. But since we're using a graph of f prime of x, what we should be looking for is where f prime changes from either increasing to decreasing or decreasing to increasing. But because I'm lazy, I'm going to say f prime changes between increasing and decreasing. So now we're looking for places where this occurs. So what I'm going to do is I'm just going to circle those spots. So we want the f prime graph to go from increasing to decreasing or decreasing to increasing. So 1, 2, 3, 4, 5, and actually 6. So there are 6 POIs of f, and there's our reason. So all I did was I again remembered the property. Point of inflections occur where the second derivative changes signs, or the first derivative changes between increasing and decreasing, or decreasing and increasing. And then I counted up the places on the graph where that actually occurred. Turned out to be 6. Okay, 14g. Find the x-coordinate of the global maximum of f of x for -6 to 0. So these questions are actually always a little bit more interesting. They add a little bit more beyond the traditional analysis we've been doing. And I'm twisting my body. I'm not allowed to do that. Sorry, I'm tired. Okay, so we're on the interval from -6, which is right here. All right, -6. Let's straighten this line out. We're going to do this right. So -6 to 0. And we're supposed to find the x-coordinate of the global maximum, or the absolute maximum of f of x. So now in looking at this, this could be kind of tough. The most common answer that people would come up with, by the way, is 7. A lot of people look at this and go, oh, 7's the biggest y value, let's go with that. But remember, we're not looking at a graph of f, we're looking at a graph of f prime of x. So we can't read it just off of the values, because what that 7 means is that the slope of f at x equals -5 is actually 7. It means the tangent line has slope 7 at x equals -5. So instead what we need to think about is what we're seeing on this interval. So what jumps out at me as I look at this is from -6 all the way to 0, do you notice that f prime of x is uniformly positive? So basically, if you don't, even so, I'm going to go ahead and list that. For -6 less than x less than 0, f prime of x is greater than 0. So let's think about that for a moment. Clearly that's true just from looking at the picture. I know there's some parts that are increasing and some parts that are decreasing. There's a little bit of both, in fact, one interval or two intervals of each. But the important thing is to note that this is definitely true. F prime is definitely positive from -6 to 0. What that means is, of course, if f prime of x is positive, that means that f is strictly increasing. And of course there's a lot of point of inflectioning happening, but we've just shown that on -6 to 0, f is strictly increasing because f prime of x is positive. We can clearly see it's positive. It's all above the x-axis. What that means is, if you picture for a second what strictly increasing looks like, strictly increasing just means it keeps getting bigger and bigger. So if that's true, and we're starting at 0, and we're ending, or sorry, not starting at 0, we're starting at -6, and we're ending at 0, the highest point is going to occur when we finish all of that increasing, or at the place where we've increased the most before we start decreasing. And in this particular case, we never start decreasing. All we do is reach our high point, or our final spot. It increases all the way to that right endpoint, which is at x equals 0. So what that tells us is that f of 0, let's see, we want the x coordinate. So what that tells us is that x equals 0 is where the max occurs. And again, you can think about this with almost any function. If the derivative is positive everywhere, that means that the slope is always positive, which means the function is increasing. If you're looking at an interval where a function is always increasing, the absolute minimum will be at the left endpoint, and the absolute maximum will be at the right endpoint. So there is our answer, x equals 0. Could also say that the absolute maximum value, if we didn't ask that, is f of 0, but we don't know what f of 0 is. They didn't give us any context for this problem, so we won't. Although later on in the course we'll be able to figure out what it is. Again, really tough question, but I know I've asked this question numerous times on exams the last few years, so be prepared. Ha, ha, ha. Okay, next question. H. Which value is greater, f of 3 or f of 6? Well, interesting. What a thinker. Well, here's what we see. People, again, let me kind of illustrate the thinking people go through. F of 3, f of 6. So people oftentimes look and they go, well, look, x equals 3 is higher. If it's higher, that means it's bigger. It's greater. Isn't that great? It was an easy problem. But no, sorry friends, that's not how this works. We're looking at a graph of f prime of x. This is all talking about the slope. All this is telling us is that the slope is 7 at x equals 3, and the slope is something smaller down here at x equals 6. To compare them, once again what we're going to do is we're going to look at the interval itself. So looking at our interval, if we're going from 3 to 6, we need to look at what's happening here. So from 3 to 6, so in fact I'll even write this out here, for x equals 3, or sorry, for 3 less than or equal to x less than or equal to 6, what I notice is that f prime of x is always greater than or equal to 0. What that tells me is that f is increasing. And we've seen this argument before, haven't we? F is increasing for 3 to 6. In fact, I'll even say that. For 3 to 6. Like literally the entire region, f is increasing. As we saw, if we have that f increasing, if we're looking for the greatest value, it's going to be further along the line. So for instance, if that's 3 and 6 occurs right over here, the higher value has to be at the bigger one. And that's literally the basic definition of increasing, is larger x values produce larger y values. I said it correctly. So that means that naturally f of 6 has to be greater than f of 3. And not just or equal to, uniformly greater. It is for sure bigger because f prime is always positive on that interval, or greater than or equal to 0 on that interval, which tells us that our y values are getting larger as we move forward. Again, another question. There's usually one question among that collection of G and H that pops up on exams here. And they're good questions to see if you really understand what this derivative graph is telling you. Okay, 14i. Ooh, yay, some sort of function redefinition. It says let c of x equal -3 f of x squared. If f of 1 equals 42, the equation of the tangent line to, oh, it doesn't say find. Holy moly. Find the equation of the tangent line to c of x at x equals 1. In fact, let me make a couple marks here. And that was write the equation. So this find, I'll put right on the actual thing. Close enough. Okay, so we want to find the equation tangent line to this thing. Well, a couple different things. First and foremost, if we want a tangent line at x equals 1, we need to figure out what c of 1 is equal to. Well, it's equal to negative 3f of 1 squared. And at first that might scare you because we don't have a whole lot of information about f itself, just its derivative. But notice 1 squared is 1, which means this is equal to negative 3f of 1, which means that our value is negative 3 times 42, which is going to be negative 126. So our y value of this function, c, is negative 126 at x equals 1. Next, we need to find the derivative so that we can talk about its slope. Like again, what we found was y1 a second ago. What we're next going to find is m. C prime of x, because of that x squared on the inside, requires the chain rule. So we're going to use the chain rule here. I'm going to do it fairly quickly though. My inside function is x squared. My outside function is negative 3f of x. So the derivative of the outside will be negative 3f prime of whatever is on the inside. Then we'll multiply by the derivative of the inside. That's going to give me a 2x times all that stuff, which gets me negative 6x f prime of x squared. Now if that's f or c prime of x, c prime of 1 is going to be negative 6 times 1 times f prime of 1 squared. That's equal to negative 6 f prime of 1. Now looking at our function, we can see over here that the y value at x equals 1 is negative 6. What that tells me, I'll do it over onto this side, is that f prime of 1 is equal to negative 6. Therefore, this is negative 6 times negative 6 equals 36. Pulling all this stuff together, we can write our tangent line equation. This will be y minus a negative 126 equals 36 x minus 1. And that is the tangent line to the graph of c of x, which required the chain rule, hence the c. See how I write things? There it is. And again, I would say, like, just kind of thinking off the top of my head, I'm doing this review video before I've actually written the full exam. I really like this question. I think that this does a good job of testing things. Now, the question would be, does this necessarily use the Unit 3 information? And I think, yes, it does. I think this is actually a really good test to see if you understand how this works, because you have to read slopes off your derivative graph, in addition to, of course, construct a tangent line using techniques we've used before, like the chain rule. So this is probably my favorite question from this whole selection in 14. So take that information for what it is. Okay, J, is that the last one? Second to last one. I really want to be done. For J, for how many values of C with negative 6 less than C less than 5 is the tangent line to f of x parallel to y equals 5x? Provide a reason for your answer. So we want f of x to be parallel to y equals 5x. So we've dealt with parallel a little bit in the past. Trying to make this clean. There we go. So if f is parallel to y equals 5x, that tells us something about f prime of x's value. That tells us that f prime of x has to be equal to what? I'll give you to the count of 4. 1, 2, 3, 4, 5. That's right. F prime of x has to be 5. So we're looking for how many different values between negative 6 and 5, which again I should probably mark this, negative 6 and 5, is f prime of x equal to 5. Well, at first you might look and go, well, there's no labels on our y-axis. But there are enough labels here. In particular, notice right here, it says f prime of x is equal to 4. So this is 4 right there. And likewise, all the way up at the top here, we have f prime of x is equal to 7. So 5 is somewhere in the middle here. So what we're trying to figure out is where along these lines, or how many different times, does 5 get crossed through on this graph between those two values. So if I draw a line here, we can actually check and see. Again, I'm not the best at drawing these lines, but let's give it a shot. So there's my line. Again, I could actually draw it straight through a little bit better and you could see it. These are all the places, anywhere where this intersects the curve, f prime of x is a place where f prime of x equals 5. So looking up here, I see 1 value, 2 value, 3 value, 4 value. So there are 4 values. And as far as the reason for the answer, I'd say that the work that I listed right up here is a pretty good explanation. I'd also say that drawing this picture, I could probably translate towards those pictures. But once again, this is one of those questions where it's great to think about, but really hard to explain and put into words. So if this were to appear on an exam, I would anticipate this to be a multiple choice style question. So it'd be less burden on the verbalizing, but the same burden on your thinking. Because again, very clever question, if I do say so myself. Never seen anything like it. I just thought it was cool. But yeah, there it is. Okay, 14K. The average rate of change of f for negative 0.5 to 2.5 is 2. So again, we're giving some weirdly specific intervals here. So negative 0.5, I'll draw a vertical line here. It's not going to be perfect, but hopefully that's good enough. So negative 0.5 to 2.5. There we go. Okay, so there's the region we're looking at. It says the average rate of change there is 2. So basically what that's telling us is f of 2.5 minus f of negative 0.5 over, what is it? 2.5 minus a negative 0.5. It says that that average rate of change has to be equal to 2. So far so good? Hope so. Okay, so how many x values satisfy the mean value theorem for f of x on this interval? How can you tell? Well, of course, if we're talking about satisfying the mean value theorem, it means that we're looking for places where f prime of x equals that average rate of change, f of b minus f of a, over b minus a. And as I look at this, unfortunately, there might not be enough information for me to really be able to tell. I think that it's going to be close. So let's see here. I wonder if I meant negative 2. You know what? Let's go ahead and assume that this question was actually meant that way. I'm going to go ahead and change it so I can have that power. So we're going to assume this is actually equal to negative 2. So given that, if we say it's negative 2, looking on this interval then, what we're looking for is how many times does it cross this value of negative 2. How often is f prime of x equal to negative 2 on that interval from negative 1/2 to 5/2? So in doing so, by choosing negative 2, it's much easier to see that there are literally 2 values. So there would be 2 values. And as far as our how can you tell, we provided that value up there. So again, I know it's kind of cheap to change the question, but sue me, it's my choice. I made the question. So I'll go fix that, take a short little break before I finish the last question on page 3, and probably call this video a day just to give myself time to rest. Well then, finally, this brings us to our last question of the day, or the last question of this part of the video, part 2. In this case, I'm just going to save the rest of the problem, part 3, for tomorrow. That last page I'll deal with tomorrow when I have a little more stamina, where my legs don't hurt, and where I'm not leaning so bad, because I haven't rested in a while and I'm not doing smart for myself. Anyway, question 15. I think this is a really fun and interesting question to go through. It's based on speculative history, so it's things that could happen. But in any event, it's just kind of a cool one to look at. And we'll try to spend some actual time talking about it, just in case this pops up. So, while returning from Bruce Bochy's final game as Giants manager, Bria hits the Golden Gate Bridge toll at 10:50 p.m. At 11:26 p.m., Bria pays the toll coming off the Antioch Bridge. So coming after the Antioch Bridge, that's like the really tall, steep one, if memory serves. 2 weeks later, Bria receives a speeding ticket in the mail. If the speed limit is 65 miles per hour for the entire 40-mile drive from San Francisco to Antioch, explain why Bria cannot mathematically fight this speeding ticket. So there's a lot of stuff to digest in this problem. And first of all, a couple details. The first one I'll mention is that while I'm an A's fan, I have respect for the San Francisco Giants manager, Bruce Bochy, who's managed for a long time. He's almost going to end his career with like 2,000 wins, 2,000 losses. So I thought first, maybe it'd be cool to put a picture of Bruce Bochy on this page. But unfortunately, every single picture I found of Bruce Bochy on Google Images featured him chewing tobacco. So while again, his choice, whatever, just disappoints me that every picture has him chewing tobacco, especially considering his good friend and former player Tony Gwynn died of cancer of the mouth because of chewing tobacco. So disappointed with that. Instead, we'll try to visualize the situation at hand here a little bit more. In particular, the story of Bria, the Giants fan, trying to drive home and getting a speeding ticket without being caught speeding. So in here, there are a couple things. First and foremost, one of the things that we have to do is we have to make a few assumptions. But before we do that, I think it'd be helpful to just kind of sketch out what the situation looks like. So I'm not sure how many of you know Bria, or if anyone does know Bria still. She graduated in 2017. She was known for driving the same car for a long time. It was a lime green Ford Fiesta. So it's a small little peppy car. So let's try to illustrate what this would look like. So first of all, let's set up a scenario here. So first place we're going to be is at the Golden Gate Bridge toll. So this will be the GG toll, the Golden Gate Bridge, or GGB. Okay, this occurs at 10:50 p.m. So helpful to start with. Later on, we have Bria hitting a second toll. So let's just go ahead and drive this over here. Go right to that far. Did I draw this correctly? I think I'm mostly at the right spot. Whatever. There we go. So in this place, though, things changed. So first, she's no longer at the Golden Gate Bridge toll, but she's just leaving the Antioch Bridge toll, and her time is 11:26 p.m. And this is all we have to basically reason here, outside of the fact that the speed limit for that region is 65 miles per hour, and that the entire drive is 40 miles. So as a heads up, I did change the problem a little bit. The drive is technically 42.9 miles. They're that far apart if you follow this pathway, as far as I can tell. But for the sake of not using a calculator, I did round it to 40. So in here, we can say a couple other things. This distance is 40 miles. Let's see, is it possible to make these things straight? Nope, definitely not. Okay, close enough. So 40 miles between her path. So she traveled a total distance of 40 miles during that time. In addition, from here, there's a couple other things we have to do. And one of those things that we need to take into account is one assumption. So we kind of have to play it like a physics game, but more than that, we've got to be a little reasonable here. Something we have to assume in order to talk about and address this question and start to analyze the speeding ticket Bria received is we need to assume that Bria's velocity, and I'll call it velocity even though we could talk about speed because she was going in one direction the whole time. We have to assume her velocity is continuous. And again, I'm hoping this isn't an unreasonable assumption to make about a late 90s model or early 2000s model Ford Fiesta, that its path is continuous, that it never at any point spontaneously teleports. Pretty sure the teleportation feature is in the 2021 model, not the 2006 model. But again, I could be wrong. I'm not a Ford Fiesta engineer. You might have to consult one of those things or Wikipedia. But for the moment, we do need to make this assumption. And I need to remind you, too, that when we're talking about velocity, velocity is equal to the position's derivative. So by saying the velocity is continuous, that's like saying the derivative of the position is continuous, which is all a different way of saying that the position function is differentiable and continuous all the way through. So that allows us to apply a particular value theorem, but I'm getting ahead of myself. So a couple other things in here. So what do we want to do? Well, I mentioned the speed thing. That's going to take into account the times. So for simplicity, I'm going to call these times t equals 0, and we're going to measure it in hours because we were talking about 65 miles per hour. And then over here, it's tempting to say something like, well, she's 36 minutes later. But we need to think about 36 minutes in terms of an hour. So if we do 36 minutes in 60 minutes, that fraction of an hour that's going to end up being, let's see, 6 over 10, which is 3/5 of an hour. So she traveled that far from t equals 0 to t equals 3/5 of an hour. So we've got all this information in place. We could also, if we wanted to, formalize one last little thing here. We could say our position at time t equals 0 was 0 and just kind of assume her path began at the Golden Gate Bridge toll, even though we knew she had to be at AT&T Park first, or whatever they call it now. And then last, we could call p of 3/5 equal to 40, because she was 40 miles away at 3/5 of an hour later. So we've got all that information. So we've also established that p is continuous and differentiable. Again, assuming that there's not some sort of Harry Potter style Hogwarts upgrade of her green Ford Fiesta. So with all this said, if we're talking about continuity and differentiability, what I'm hoping that starts to scream to you is the mean value theorem. This is actually a mean value theorem sort of question, or at least we're going to need to invoke the mean value theorem to draw some conclusions. So in here, what I'm going to do for the mean value theorem is I want to talk about the average rate of change of f of x being equal to f prime of c. So in our case, we've got to think about our function. We're going to let f be the position function. So in reality, what we want to be able to conclude is something about p of 40, or sorry, I lied, p of 3/5 minus p of 0 all over 3/5 minus 0. So what we've just calculated is her average rate of change of her position, which is the same thing as what we call her average speed. So her average speed over that interval was 40 minus 0 over 3/5, which is 40 over 3/5, which is 40 times 5, which is 200 over 3. And for simplicity, for 200 over 3 is 66 2/3. So take that into account. We found that her average speed on that time interval was 66 2/3 miles per hour. Now what we can use though is using because we have the guarantees of continuity and stuff, using the mean value theorem, we know that our average rate of change had to be equal to our derivative at some point. And in our case, since we chose p prime is equal to her velocity. So that means that Bria's velocity at some point during her path had to be 66 2/3 miles per hour, because the average rate of change, 66 2/3 miles per hour, has to be equal to the instantaneous rate of change, her literal speed, at some point on that path by the mean value theorem. So what that means is, so Bria's velocity, which we can probably call speed here safely. I mean, if she went backward, that meant she went even faster, so it should be speed. So Bria's speed was 66 2/3 miles per hour for some t between 0 and 3/5. So basically, at some time between 10:50 p.m. and 11:26, Bria was going 66 2/3 miles per hour. We don't know when, we don't know for how long, but we know she was. What that means is that we can then take into account the fact that the speed limit of 65, unfortunately, 65 is smaller than her speed at that instant. So unfortunately what that means is Bria earned the ticket. Unbelievably, for some reason, I don't know, the Highway Patrol or the police are checking that region of the thing, looking at fast track data and all that good stuff. They want to award a ticket for someone going 1 2/3 miles per hour over the speed limit. But again, we're not one to judge. That's not my job here. I was the person who advocated using the intermediate value theorem to get out of long extended stops and stop signs, so who am I to talk? All that matters is the mean value theorem itself guarantees us that there's at least one time where Bria's velocity exceeded the speed limit, and that is enough to qualify her for a speeding ticket. Of course, it doesn't mean you have to speed for 20 minutes or anything. You can just be clocked and radared at one point. And unfortunately, her tolls, which literally take into account the time that she pays them and gets into them, prove that she was exceeding the speed limit at least once. So, with that said, I'm going to end this part 2 video because I am exhausted and beat. So hopefully this has been helpful. I actually really enjoyed the last question the most. In fact, I'll probably be, where's my phone? I will be taking a picture of it to send to Bria here. But with that said, hopefully the second part has been helpful too, and you've gotten some good work out of it. Again, I'll return tomorrow with part 3. Thank you for watching. Have a good night.